All right, how's everybody doing today? I'm gonna get started. Sorry, it took me a minute to get my ducks in a row right now. So today we're gonna continue on with Kepler and Newton, and we're gonna get into the derivation of Kepler's laws from Newton's laws, which is one of the triumphs of, I think, human uh, knowledge and skills. So let's see, what are we doing today? Let's get through the bookkeeping first. Okay, I had forgotten to say, and several of you had asked, and I need to say, I want to make sure that I say it again for everybody. On the final, you're allowed to have one sheet of paper, front and back, 8.5 inches by 11, standard sheet of paper. Nothing funny. I had one student so there's a lot of tables in the book and in one of the other classes I teach, and one of the students had Xeroxed all the tables and had taped them like scales onto her 8.5 by 11 sheet of paper. So she had all these fold-up things, and it was awesome. She was like, "Does that count?" And I'm like, "No." But so 8.5 sheet by 11, whatever you can write down on it. We'll talk more about what to put on that later. But really, that's a crutch for you. So you don't have to memorize all of this stuff. Yeah.
Is printing acceptable? Like if you print stuff on
Yeah, sure, totally. I mean, yeah, as long you may not have a magnifying glass, so
Okay.
don't print it so small you can't read it. Okay, reading today. Let's go through the reading. So we're gonna go. So there's a reading due today, which most of you got in, and I appreciate it. There's homework due Friday. I hope everybody saw that. I feel that I got it out in time enough to not change the deadline because I don't want to have to move the deadline of the homework. So if the fact that I didn't get it out till the middle of Saturday causes anybody undue hardships, let me know. But I'll have office hours on Thursday. So this homework really sets the tone of what I'm looking for in a lot of ways for the class. So some of the things in the class. Oh, one of the questions is just plot a bunch of stuff. I figure everybody here has skills at plotting a bunch of numbers. If you don't have, like if I say, hey, plot these numbers and make a line, and that's a giant headache for you, come talk to me and I'll hook you up with a Jupyter notebook that'll make that easy for you. Other than that, there's a plotting thing that you can just use whatever you like to plot if you have a favorite plotting software. Let's see. So I'm going to finish up what I was saying about ellipses and Newton's gravity. I'll talk about the acceleration of gravity on the Earth and the fact that spheres act as points. I'll explain that in a second. I'll talk a little bit about work and energy, and then I'm going to get into the derivation of Kepler's laws. So probably not going to get through all of this today. If I do, it won't be a very good lecture. So let's hope that I don't. Okay, so a whole bunch of you had asked, please go over the derivation of one of the things that there's derivations that are in the book. So this reading was heavier than the previous readings. There will be readings about this heavy in the future, probably nothing heavier than this, but there will be some sections with math and some sections that don't have as much math. Sometimes there's going to be plenty. So the things that I care about, so how deep do you need to go down that rabbit hole while you're doing the reading? You don't need to go very deep. I don't expect you to come out of the reading with a thorough understanding of these derivations. I don't really expect you to understand all the details of every derivation until I have made you go over it again. So the derivations that I want you to be intimately familiar with, some of these derivations I want you to understand pretty well because they connect important pieces of physics. But I'll explain which ones, and I'll make you do them for homework. So the ones that I really want you to care about, I'll make you do for homework. Does that make sense? Several of you had asked, how many of these am I going to be on the hook for? Then the answer is some of them. That being said, I know how long it takes you guys to do stuff because I ask you all the time, right? How long it takes you to do stuff. So I'm not going to give you a derivation on the final that I don't think that you can actually pull off. That wouldn't be cool. So. Was that?
That would be mean.
It would be rough. Okay, so let's see. That was a lot to unpack. I look forward to going over a class that was a good one. Several of you said this was a confusing section, which is actually understandable because there's a lot in it. It's pretty heavy. Okay, and then are we expected to be able to do this derivation from memory? No. I don't really want you to memorize anything other than the core pieces of physics. I want you to be able to derive everything from that. That's how I think that you should do physics. But when you're doing the reading, just read it like a novel. And if you don't understand the derivation, just write down, I didn't understand that derivation. Could you go over it? And I'll go over it if I actually care about it. This question was on the virial theorem. Do we need to know how to prove the existence of things like it did in the book, or are these things that we should just accept blindly? I want you to be able to follow all the derivations, not necessarily reproduce all the derivations, and not necessarily the first time. Like the first time through it, if you don't understand it, that's okay. But I want you to understand it when you go over it again, when I talk about it. When I talk about the derivations, at that point, by the time I'm done talking, you should have followed everything. And if you didn't, stop me and I'll go back and do it again. But the connections of the fundamental physics to the observational quantities are really one of the things that I want to get out. So I don't want you to accept a single thing that I say as blind truth. I want you to say, yeah, prove that to everything that I say. And sometimes the answer is going to be you have to take XCal for the actual proof, but at least ask, right? So don't accept anything blindly. Make sure that you at least understand what pieces went into the proof and what pieces came out of the proof. Sometimes you don't understand the whole proof itself, but you at least understand, okay, we started with angular momentum conservation, and we ended with things move on an ellipse. I don't get all the details in the middle, but the important bits are what went in and what came out. Okay, angle brackets do mean average, so this angle Q is the average of Q over a certain system, over everything that it can. What is reduced mass? So this whole stunt is taking a thing that's got two objects in it and getting rid of one of them because I don't actually have two objects worth of information. I'll explain that in a minute. But the reduced mass is a way of turning two things moving around into one thing moving around, or two things moving around, but the only thing I care about is the separation between the two of them, not their individual positions. So the reduced mass is like a stunt. It's like a math thing that we use, or it's the harmonic average of the two masses. So there's a couple ways to do an average, right? So the easiest way to do an average is just Q1 plus Q2 over 2. Just add them up and divide by the number, right? Or I could do the harmonic average, which is 1 over Q1 plus 1 over Q2, which gives me units of 1 over whatever thing I'm looking for. That's not what I want. Raise all that to the minus 1. So 1 over the sum of the reciprocals is the harmonic mean. This, if you do the average, is Q1, Q2 over Q1 plus Q2. This is another way to average things. The last way that people like to average things is the geometric mean, Q1, Q2, square root of those guys. This is another way you can take an average. It's like a product average. This is like a reciprocal average. Yeah?
Do they all come up with the same answer?
No, they come up with different answers. That's a great question. They all come up with different answers because you're taking the average in different ways. You're asking different questions. So the reduced mass is kind of a stunt, but it's a way to simplify things. How do you get from the binary system to the displacement vector? That I'm going to spend a minute on. And R versus R prime, that's again, when we start the problem, we have two vectors that we need to worry about, the positions of both of the planets. But I don't really want to do that because I'm lazy, so I'm going to get rid of one of them. So R prime is the other planet, but I get rid of that. So I'll explain all that in a minute. What is this Q in the virial theorem? It is, so the quantity they define, is this big Q, which is the sum on the momentum times the position, which by itself is not really a quantity that I know a ton about. It's a spatial weighting of the momentum. It's like an average momentum. I don't really have great physical intuition for this, and also I don't derive the virial theorem the way he does it in the book. The way I do it is better and makes more sense. So I'll do that for you. And we don't need that Q, which doesn't make any sense. I will go through the virial theorem slowly. Probably not today. It's probably going to be Wednesday when I get to that. Are we easily able to substitute the general mass for the individual masses? So you've got to be careful. So what I'm assuming is we've got all these things that look like big M is the sum on little m. So here I'm just adding up all the little m's. Can I just in general write an equation for this thing as well as for this thing? No, not really, but kind of. So in the book starts off talking about how to deal with the ensemble instead of the individual points in like a collection of stars. And sometimes you can deal with the whole mass. Sometimes you need to deal with the individuals if you're looking at the actual gravity. So if the configuration matters, then you need to deal with the individual masses. But if the configuration doesn't matter, you can treat everything at once at the same time. So for instance, if I'm thinking about all of the stars in the galaxy, lots of them are binary stars. I don't need to know that they're binary stars. It's just one star at a point. But if I'm orbiting those stars, then I do need to know if it's a binary star. So it depends on what you're doing, and you have to be careful. So the answer is kind of yes for this one. I will go through that derivation. One of you is looking for additional readings on derivation. I would say more textbooks on physics. I don't have a great answer, but read more physics textbooks because it'll become clear, especially as we go through this course. The importance of Kepler's laws will become important. And how do we use and apply Kepler and virial? I'll show you. So virial theorem really boils down to something very simple. When I use virial theorem, I'm going to tell you that v squared equals gm over r. And what this does, so this is the kinetic energy, right? Oh yeah, I'm missing a half and an m, but I don't care about that. And it's twice the kinetic energy, so that's where the half goes. And the energy is gmm, but I got rid of the little m because it's over there, right? I got rid of the m. So just gm over r relates the mass of an object with its size and its velocity. So this is what comes out of it. And this relationship is very useful because if I say, okay, I've got a sun, I've got a star that's, say, 10 solar masses, and I'm orbiting at a distance of 4 million AU, then how fast am I going? That's how fast I'm going. So virial theorem is a really great way to connect different pieces of the system.
In that case, the big M would be the sum of the two masses? Or
no, big M is going to be the thing that you're orbiting, the central mass. So it depends on how you write it down. So if I've got a star that's orbiting, if I've got a planet that's orbiting a star, then it would just be the central mass.
Oh, so the small m doesn't even matter?
Small m canceled out.
Okay.
So this is hand waving. So I'm going to put air quotes around this, right? This is me waving my hands because this is some kind of average velocity and some kind of average mass and usually some kind of average radius. So this is a little bit hand wavy when I use it because we're going to make some assumptions. So sometimes the differences between which mass I'm using really matter, and sometimes you just need something that's approximately right. Okay. Why do we use reduced mass? So we use the reduced mass as a simplification tool that I'll explain in a little bit. What does it mean? I don't have it's the geometric mean of the two. And it doesn't provide a more general way to do things. It provides a simpler way to do exactly the same thing. So I can do two bodies orbiting each other by hand, but that's a headache because I only have one position that I care about. Let's see, I will explain the virial theorem and why it works later. Does the virial theorem help with anything besides orbits? Yeah, the virial theorem applies all kinds of places. As we'll see, and you'll see again in XGAL, that this combination of things shows up all over the place. If I'm looking at a galaxy, the same is true. If I'm looking at a cluster of galaxies, the same thing is true. Let's see. Yeah, in the center of mass frame problem, is the new center frame assigned so that you can choose a coordinate system where the center of mass is at rest? Yes. That's exactly right. So we're going through all of this so that we can cut out degrees of information. I'll explain it in a little bit more detail. In the derivation of the virial theorem, do we need to substitute the formula for gravitational force? Yes, it's not always gravitationally bound, but you always need to use the gravitational. Well, you don't always need to use the gravitational force. You can go through the same process with your generic forces. Then it becomes a thermodynamics problem, which is outside the scope of what I'm going to do in this class. But yes, virial theorem is very broad. Okay, any other questions on the questions? Everybody good? I'm going to jump right into it. Okay, ellipses. So the thing that I didn't quite get to with ellipses is this bit here, which I'm going to make you derive for homework. So one of the homework problems is prove this, and one of the homework problems is prove this. And I think that this one is important. They're both important, but this one is important. This says that the radius, if measured from the semi-major axis at perihelion, so now the coordinate system is relative to this focus and perihelion, and the angle is measured from perihelion. And I'll show you when we do the math, it'll just naturally come out that way, but we're just going to do it by hand because that's the easiest coordinate system to take. So if theta is the angle from the semi-major axis to where you are, this is the position r. Forget about r prime now. We don't need that one. Well, we'll need it in a second for a minute. But r follows this circle, and r gets bigger as theta increases. So as I go around the circle, r is the semi-major axis times this kind of confusing quantity, but this is just a shape parameter. So this is just how oblong it is, 1 minus epsilon squared, over 1 plus epsilon cosine theta. So the position information comes in this cosine theta. So one of the questions that I got more than once was, where do the aphelion and perihelion formula come from? Because it had, the book has written down r at perihelion is this, and r at aphelion is that. So perihelion is just what? It's just plugging in cosine of theta equals 0 here, because that's going to get you this point. And then cosine theta equals pi gets you this point here. So so that's just a 1 and a minus 1 down in the denominator, because the cosine changes from 1 to minus 1. But this equation, this describes not just an ellipse, but all of the conic sections, kind of in general. So hopefully you did this when you were in algebra, but this equation describes 3 kinds of trajectories. So it describes ellipses, parabolas. Where'd my chalk go? Okay. Ellipses, parabolas, and hyperbolas. And where's my arrow? There it is. And you can think of these. This is not actually useful unless you're doing math, but you'll hear it a lot, and the book talks about it, so I'm going to spend 9 seconds on it. I've got this equation, and I can think about this equation as being ellipses, like that, which if I think about a cone, so if I take a cone and I cut it off, so here's the axis of the cone. If I cut the cone off perpendicular to the axis and I look at what I get what? What kind of shape is that?
Circle.
That's a circle. If I cut it at an angle, what kind of shape do I get?
Ellipse.
That gives me an ellipse. If I cut it so that my cut is on all of one side of the axis, then I'm left with a shape that looks like this. What's that one?
Parabola.
That one's a parabola. And if I do it at an angle like this, but I don't cut the side, if I cut through the side, then I get an ellipse. If I don't cut through the side, I get a hyperbola. And that describes the 3 kinds of orbits that 2 things have. So if I've got 2 objects, I've got a planet and a star, or whatever, it could be 2 galaxies. If the 2 things are gravitationally bound, their orbit is an ellipse. If they're not bound, and I mean really not bound, then their trajectory is a hyperbola. So I have one star here, my other star is going to come in and hook around like that, and that's a hyperbola. And the thing that's exactly between a hyperbola and a parabola, and an ellipse is a parabola, which is also an open circle. So parabolic orbits very rarely happen because that's a very sweet spot in the binding. That's exactly not bound, but that's such a rare spot that you never see a parabolic orbits. They're going to be hyperbolically scattering off each other, or they'll be bound in an elliptic orbit. And this is true for anything. This is true for electrons and protons too. This is true for a sea of electrons. If I shoot an electron into a sea of electrons, it'll behave the same kind of way. I can get two bound electrons, and they'll be in an elliptical orbit. They'll be quantum mechanical, so they're not actually going to do that. Yeah.
If something was passing with a, I don't want to say parabola. I guess I would say parabola. If something's passing an object with parabola, like orbit, like it's perfect. Would it end up slowing down a bunch afterwards?
It'll come out with the same speed it went in at.
Oh, okay.
So all of these, that's a good question. So if I've got a trajectory like this where I come in here and I hook around and I come back this way, so this is just like I throw a ball up into the air and I measure its velocity. So it's got the velocity that it leaves my hand with. What's the velocity that I catch it with, that it has when I catch it? Same velocity. So it starts off with some kinetic energy, it dumps it all into potential energy as it gets high, then it comes back down and it gives me back the same velocity. And that sums up even the elliptical orbits too. So down here is like being at the bottom where the velocity is high, and then we get hooked way up here where the potential energy is high and the velocity is small, and then it comes back down. So we have this trade-off of velocity and energy, but the velocity, if you get to the same potential point, will always be the same. Yeah.
And is that the same with hyperbola?
Yeah. They'll all be symmetric. Yeah.
Sorry.
No, it's all good. Yeah.
Do you have to, like, how do they do slingshots then? Like, they don't, they don't add velocity?
No, that's right. This is fixed.
Oh.
What's the difference?
Okay.
The difference, so that's a really good question, right? So this is a really good question. So how does a slingshot orbit work? If I'm right here and I go like this, if this thing is fixed in this universe, or it's free to move, but it's not moving by itself, right? So in my universe, these two things don't have any external things. Then when they hook past each other, when you get back to the same distance, you'll have the same velocity. So how does a slingshot work? So with a slingshot, what we do is we shoot a satellite at Jupiter, and we use Jupiter. We have I think it has to be perfectly parabolic for the slingshot to work, but I'm not 100% sure. It's not a bound orbit, so it's not elliptical, but we shoot a satellite at Jupiter, and we get Jupiter to hook it forward to get it a lot more energy, because what happens is Jupiter's moving like this, the planet comes in like this, and then goes out like that, and here, Jupiter has slowed down a little bit, and the planet has been given a kick. So, slingshot orbits are intriguing, and they're a little bit complicated and counterintuitive, but it's the fact that Jupiter's moving. Vlad, you had a question.
When we're doing elliptical orbits, we have to account for like the second focus moving, because does it always stay in the same place?
Yeah. That's another great question. Why will the second focus always stay in the same place? It's a good class question. Somebody yell something.
Because like, I don't know, I've just been playing around with like orbital simulators, and like you tend to get orbits that are like weird shapes where the second focus just keeps moving around.
Well, it depends on how you set it up. So if you set it up with just two objects, then they will always orbit one plane, and the two foci will be fixed in space because the angular momentum is conserved. But if you have a boundary condition or you have multiple objects, then you'll get weird things. Yeah.
So it just happens to be that force from other planets just move it slightly, so the focus.
Oh, if like the objects have initial velocity, like in different directions, that could affect it?
Yeah, so all of this works once you've boosted to the center of mass frame. When you're not in the center of mass frame, things are going to move around in weird ways. And they'll be orbiting the center of mass. So they'll look like they're doing weird crap, but if you tie your brain to what the center of mass is, they will always be doing something reasonable. Does that make sense?
Yeah.
Because that's the stunt that I'm going to pull right at the beginning. That's not necessarily obvious, and I'll do that in a second. Let's see. Did I finish all the questions? I did.
We were on ellipses.
Was that?
We were on ellipses.
Yeah. Okay, so this is the important bit. Any other questions on ellipses? We'll talk about them kind of ad nauseum, but I think that those are the important bits that I had to say. And okay, Newton's 3 laws, which we talked about. Okay, let's talk about gravity for a minute. Sorry, I'm strategizing based on what the clock tells me. Okay, so gravity, the force between 2 points is the product of the 2 masses divided by the distance squared. And then there's a constant for units, because God didn't tell us what units to use. But the force is equal to minus G M1 M2 over R1 minus R2 squared. This is a vector norm times R hat, 1, 2, the unit vector between the 2. So, okay, dumbest thing possible. Well, okay, so one cool thing, if I have an object, say I've got a planet that I'm sitting on, say this is the Earth, and I'm standing on the surface of the Earth, I can sort out what the acceleration due to gravity is. The acceleration due to gravity is just the force over the mass, and that's cool because the force depends on the mass for everybody, so the acceleration is the same for everybody. That should be familiar. If that's not familiar, stop me and I will go say it again slower. The acceleration from a planet is the same for every object. And it's equal to just F over m, so that's equal to some number g times the mass of the planet, and that's it, divided by r squared. So, if I want to sort out, so what's the acceleration due to gravity from the planet when I'm standing on the surface? Everybody can yell it out. 9.8 meters per second squared. Those units are important because 9.8 only matters in meters and seconds, right? But you get 9.8 meters per second squared if I put in what? I got to put in this Earth's mass here, and the Earth's radius here. And then I just crunch it and I get 9.8 meters per second. And I got another question for you. Let's do a little math in our head. So what about the International Space Station? You got a question before I move on? Was that? Oh, when I write this down, I'm going to write this down in a bunch of different ways, and I'm going to be really sloppy about notation because I'm going to apply it to the thing that I'm looking at, which sometimes I'm going to use a big M, sometimes I'll use a little m. It just kind of depends. I'm a little sloppy with notation. I try to be consistent, but you just get 1 M there. Yeah. It was a good question. Okay, everybody got your voters. And I got a voter question for you. So, what does an astronaut feel on the International Space Station as far as their acceleration from the planet? So the options are 10 meters a second, 0.98 meters a second, 8.7 meters a second, or 106 meters per second squared. Everybody don't get a calculator, do it in your head. I know you can't do that in your head because I didn't even tell you what G is, but everybody give it a guess. Give you like 5 seconds and then vote. All right, everybody ready? I should make everybody vote at once. That way, yeah. Okay, hold it up. Okay, so we got, all right, little column A, little column B. Okay, talk to your partner or whoever's sitting next to you. Tell them what you got and tell them why you think you got what you got. So we'll spend like a minute talking about it.
Well, aren't they floating on the ice?
Yeah, well, it's obviously
They call it microgravity.
so I just took it as
I feel like Maybe be that.
It's just
Maybe it's like
You know, it can't be more, so it can't be different.
maybe some ISS.
I mean, I don't think it's gonna be that close, because otherwise it would be yeah,
They're floating.
yeah, I know, but he just feels really small. Especially because all things considered, the ISS is because like my thought is if it was that close and it was 0.98, it would be like 0 where the moon is.
Well, if you think about it, if you look at it like this, like I'm just trying to emphasize it like where they
Okay, that's been a minute, so let's vote again. Everybody take a second. Vote in 5, 4, 3. There you go. Oh, some people changed, but not. Okay, some people improved and some people didn't. All right. Not everybody converged. That's okay. So the right answer is C. So we had a mix of C and B in the crowd. So okay, that's bigger than 9.8. Why is that wrong?
It's at a greater radius.
It's at a greater radius, so this goes down, right? It's not D. I don't think anybody said D either, because that's a lot bigger, right? How about B?
Too small.
Yeah, this is about 0.
They do call it microgravity.
They call it microgravity, but it's a dodge. You experience microgravity because you don't actually feel the thing. So the correct answer is C, because you can think about the math. Just think about the math. So I got this number that's like 9.8, right? So it's like something divided by 6,000 squared gives me 9.8. Now I'm going to divide it by 6,000 plus 400 squared. Not a very big difference. So the astronauts are feeling basically the same gravity that you feel on Earth. So what's the difference? So you can see a cartoon of this, because the space station is closer than Atlanta, right? The space station is not actually that far away. Space is pretty close. If I drew this to scale, they're like here, right? That's not a big difference. So if you think about this, yeah. So if you think about this like a Taylor series, we can say that the force is going to be 9.8 times 1 minus r Earth over r astronaut squared. And if I do a Taylor series, I see that I've got something that winds up going like r astronaut over r Earth, which is a very tiny number. This is 400 kilometers and this is 6,000 kilometers. And it's actually shows up squared. So the difference is this little quantity. So, okay. Now, oh yeah. Okay, I'm going to spend all the rest of my time on this other derivation. So one of the important things, and this is kind of ugly math, you're not on the hook for this derivation. I'm not going to expect anybody to go through this because it's ugly and we don't get a lot out of it. And I'm actually only going to give you like 80% of the proof because part of it is boring. So so let me put up what I'm talking about. So we're going off of page. What page are we on? So this is the page 42. Okay. So I'm going to leave that up, but I'm going to talk over here. So what this section of the book says is that if it's spherical, I can treat it like a point. Oh, actually, sorry. I forgot to finish up why astronauts feel weightless. I should have done that. Why do astronauts feel weightless? We just said that the gravity is basically the same.
Because we're used to the gravity 9.8, so it feels a lot less when you're up there, even though it's not.
No, they really do experience no force against the walls of the space station. Yeah, because they're in free fall. Because they are both, yeah.
The centrifugal force cancels out the gravity.
That's another excellent way to think about it, is the centripetal force is canceling out the gravity. So, everybody's spinning around this way, so you can think about the centrifugal force as going out that direction. That's equivalent to the centripetal acceleration. Another way to think about it is, if I've got, say I've got a sphere like this, right? If I launch something from here, it's going to fall in a parabolic arc until it hits the ground. Right? That's going to be my parabola. If I shoot something up like this, but the Earth falls away, then it'll hit the Earth, but it'll hit way over here. But if I shoot it fast enough, so that the Earth is effectively falling away at the same rate that I'm going, then I'm falling down, but as soon as I move, I'm falling this way, but as soon as I start to go this way, I'm over here, and the ground is lower. So I haven't actually gone down any. I've gone down, but I've also gone over, so down doesn't count anymore. If that makes sense. I don't know if that's a useful. Yeah.
How perfectly circular is the ISS orbit?
I don't know. Not particularly, because it comes up and down, so it drifts inwards because of drag from the atmosphere, and periodically gets pushed outwards by, well, it used to be the space shuttle.
Isn't it still in the atmosphere?
Yeah, the atmosphere is actually huge. So where does outer space start? That's an excellent place for a debate, because it's not really obvious where outer space starts, because there's not an edge to the atmosphere. This atmosphere falls off exponentially.
It's kind of at 100 kilometers.
Yeah.
Not really.
That's right. So 100 kilometers is a good ballpark, because that's the Armstrong line, which is where water starts to boil. So where water starts to boil because the pressure's too low is where you can not survive, like hard, not survive. But that's squishy because there's still plenty of atmosphere there. You're still within the Van Allen belts there. So outer space doesn't really happen until you're outside of the Van Allen belts. You can really see the sun and solar radiation. So anyway, okay, I got enough time to do this, right? Yeah, okay. Okay, so this works because the Earth has some size, but what I really want is to not have to worry about the fact that the Earth has shape. So one of the cool things, this is called the shell theorem, and what it says is that if the object is round, then I can treat the object's gravitational force as though it were a point at the center of the object. If round, then point. I could put more words up there, but I don't need to do that. So if the object is actually spherically symmetric, then I don't have to worry about the fact that it's a shape, and I can just deal with it as a point mass right here. So what we're going to do is go through the proof of that, and all I'm going to do is set it up. I'm going to skip some of the algebra because it's a good way to get lost. It's not very interesting. And it's actually hairy algebra, like it's not my favorite algebra. So here's me. I'm not actually that big, but I'm at this position. And I'm feeling the gravitational force from a planet. So what I'm going to do is I'm going to say that I'm going to compute the force. Remember, force is a vector, so we'll treat it like a vector for a second, which is equal to the sum on all of the little points. G mi times m me. So this is m me. And mi is every little point in the sphere. I'll be more systematic with it in a second. Okay. Sum on this divided by r minus ri squared. Okay. So what I'm going to do is I'm going to compute the force on this point here from all the points in here in a consistent way. And what falls out is I can treat it as all of the mass is just at this point here. So the distance between my test and the center, we'll call this R. Now, I'm going to think about a little point of mass here. I didn't intend for that to be my node, but now it is. That's awesome. So this little test mass here is at a distance s from me. So what I'm going to do is integrate over all of these s's. So I've got this complicated formula, which is a sum over all my masses. I can turn this into an integral. I'll turn this into an integral in a second. Or I could say that F equals m total times me over r to the center squared. Then there's a minus g up front. So I can either have sum everything up or just the total mass times my mass times g. So this is going back to one of your questions. When do I have to use all the bits and when do I need to use the whole thing? Here we have to show that I can use the whole thing instead of all the bits, but then we can forget about it. You have a question?
What's this squiggly line symbol?
This?
Yeah.
This is a sum.
Oh, okay.
Yeah. You have a question?
Do we need the unit vector?
Oh, probably, yeah. Oh, man. Some R's. Okay. Yeah, so there's an R hat, but I'm going to get rid of that in a second because I'm going to deal with the two forces individually. Okay, so let's pick a coordinate system. I'm going to use a couple of different coordinate systems. For a second, I'm going to use X, Y, Z. So X is along the R vector pointing between the test mass and the center of the planet. So I know that Fx, the X component, is going to be something complicated that I have to work out. Fy, however, is not something complicated that I have to work out. We can see that Fy is something easy. What do you think it's going to be? If it's easy, it's 0. Right? 0 is the easiest number to deal with. Fy is 0. Why is Fy 0? So now this is the transverse bits. So why is the net Fy equal to 0 for this object?
Because there's a point equal on the other side.
Did everybody follow that? So I've got this point here, but then I've also got an equivalent point over here. And this one is going to give me a force in this direction and a force in this direction. Sorry. This one will pull, and this one will give me a force in this direction and a force in this direction. So okay, the arrows will change sign if you're looking at the other thing, but the fact that I've got a y force that's pointing up from this one and a y force that's pointing down from this one means they're going to cancel out. So I don't have to worry about the force in the y direction or the z direction, because as I rotate this, there's always a pair of points that cancel each other out. So I don't need to worry about the this way force. I only need to worry about the this way force. So now I can drop the unit vector. And we'll talk about, let's not talk about a point, let's talk about all the points on a ring at a certain radius. So this is at a certain radius r from the center, right? So what is this picture supposed to be? Okay, if I flatten it and I don't try to give it any perspective, this is this point, and then in a ring, it's all the points at a certain distance away from the center at a particular angle. We're going to call this angle theta. Does that make sense? Does the geometry of this make sense? So I'm going to think for a second. So I've got a sphere, and I'm just going to carve out a ring of points that are all at the same angle and radius from the center, because they're all the same as far as my test, as far as I am concerned, where I'm trying to measure the force. So we're going to deal with this whole ring at once. So, where are we at? So the force from this ring, the force from a little patch of this ring, we're going to call this dF. Okay, d anything means tiny. That's pretty consistent. If I have d whatever, that means an infinitesimal thing. That means it's vanishingly small. That means it's as small as I can make it. 0, but not really 0, but calculus 0. So not actually 0. This is infinitesimal. Because this is infinitesimally thin, I don't want to have to deal with the thickness of my ring. It's just a ring. It's going to be minus g times my mass of d, times dm ring over s squared. Times, no, that's not right. That's not quite right. Because I'm only looking at the x component. What am I missing? I'm missing cosine of phi. So I need gravity, my mass, the mass of the thing that's giving the force, the planet, which now is dm ring, that's a ring, times cosine of theta, because we're only concerned about this component of the force. Pretty good? So, so we need to have two things that we need to figure out. We need to figure out what dm ring is, and cosine phi, I don't want to use this coordinate system. I want to use a coordinate system that's centered on the planet, because I don't know where I'm going to be, but I know where the planet's going to be. So the coordinate system centered on the planet is going to be r for radius. We can call it theta is the angle towards me. And we'll call it phi prime. I'm going to call it phi prime because I'm going to get rid of it really fast. That's the angle around this direction. So d mass is going to be what? It's going to be the density, r. So we're going to assume that this sphere has a density, rho, that depends on radius, but nothing else. Now, if it depended on anything else, it wouldn't be spherically symmetric anymore, and all of this would break down. So dm is the mass density times the volume element, right? The volume element in spherical coordinates where I got oops, actually the way I'm drawing it now, this one is going to be phi prime, and this one is going to be theta, and then I'm going to be up here. My test is going to be up here. So my coordinate system is, how much is small? So my coordinate system is theta, the pole is pointing at me, theta is the angle away from me, and phi is the angle around it. If I take a little patch of volume is a little wedge. And the volume of this wedge, dV, is equal to dr, d phi, d theta times something, because these volume elements change as I move around in the sphere. Why is that? Times r squared sine theta, or d phi theta. So why is that? Because when I'm up here, my two little, the volume of this area is small. So I've got to divide it up by something small. So sine theta takes care of the volume of the element as I move this way, and the r squared takes care of the fact that as I go out this way, my volume changes as well. So two radii look like this. One volume element is here, another volume element is here. This guy's bigger, right? This is just bigger. So the volume element in 3 dimensions is r squared sine theta times dr d phi d theta. Uh-oh, I ran over. Anybody got anywhere to be? I can keep going, or I can stop. Probably should stop. Okay, so this is where we're going to set up. So let me quick outline what I'm going to do, and then I'll pick it up on Wednesday. Okay, so we're going to write down the mass element. dm is just density times dv, and dv is just this business. Okay? It's just geometry. We integrate over phi prime. This one is prime, which just gives us 2 pi. So then all I have is r and theta. What I care about is phi. So I do a little geometry to relate theta to phi. So we need to get rid of this phi here. And we need to deal with the volume elements here. And then we do a u substitution. So all we do is we change the geometry so that we get rid of s, because this depends on s. I don't want s. I want these coordinates. So we get rid of s. We get rid of phi. And that makes it ugly, but not confusing. It's just ugly because there's a lot of geometry in there. And then you do a u substitution. And then you do a little bit of algebra, and what you're left with is, so this is ugly, but the force that you're left with is just minus g times m times my mass over r, which is just this one. I may or may not actually follow through with that, depending on how people care. I don't really care about this derivation too much. I care about the result, but I don't really care about the derivation because it's just calculus. But if anybody is still unsatisfied with this, let me know.
So this one is just some algebra and a triple integral.
Yeah, it's just, so there's a triple integral and a little bit of algebra to make the integral work, and then you're done.
Okay, that's not bad.
Yeah.